Hello, and welcome to Hive Learning Channel. I am Aaron Francis Gumapon, your teacher for today's video. And in this video, I will be talking about fructose, its sweetness, and metabolism. Without further ado, let's get right into it.
But before we begin, I will be giving you all a drill to participate in. Here is the drill. Recall and list down all the characteristics of fructose. When you think of fructose, the first thing that you might think of would be that it is a sugar, a monosaccharide, just like glucose. For the special learners watching, you might say that it is in fact the sweetest sugar, and that it is also a ketose. For those who do say that, I applaud you for your prior knowledge. Now, let us keep these ideas in our mind as we tackle this topic. We will soon find out how all these things connect. Let's now read the learning objectives. First, describe the structure and chemical characteristics of fructose as a monosaccharide. Explain the basis of fructose's perceived sweetness compared to other sugars. Outline the major metabolic pathways and health implications involving fructose in the human body. Now, let us start with our first question. What is fructose? Fructose is a monosaccharide with a molecular formula of 6 carbon atoms, 12 hydrogen atoms, and 6 oxygen atoms. It is characterized by a ketone functional group located in the second carbon atom, making it a ketohexose. When observed in the laboratory, you will also find that pure fructose is white, sweet, and colorless, with a high solubility in water. Now, learners, did you know that fructose is actually the sweetest monosaccharide? As demonstrated by my assistant Kenny here, we have a table showing sweeteners and their relative sweetness values. As you can see in the chart, fructose is the sweetest of all naturally occurring sugars, with it having about 1.2 to 1.8 times sweeter than sucrose or table sugar, and roughly twice as sweet as glucose. Now, you wonder, why is that? Why is fructose the sweetest? Well, that is because of fructose's structure. It better matches the binding sites on sweet taste receptors, causing a stronger and longer lasting activation of these receptors compared to glucose or sucrose. To add to that, research shows that fructose forms shorter and stronger hydrogen bonds with surrounding water molecules than other sugars. This property is believed to influence how fructose interacts with its sweetness receptors, enhancing its perceived sweetness. Now that we know what fructose is all about, we would probably wonder, where can we find this sugar around us, especially in our food? In this next slide, we can see the foods that could contain fructose for us to eat. In the slide provided, you can see fruits such as apples, cherries, mangoes, and raisins. We also have vegetables here, onions, and asparagus. Other things show honey, fruit juice, and this bottle in the leftmost with a corn design in the label. That, my learners, is high fructose corn syrup. That is a common sweetener used in commercialized processed foods that need a little sweetness for the masses. From sweets to sodas like your Coke, or even your snacks like Twinkies, you can be certain that in the ingredients label, you can find fructose corn syrup used to make them. Because fructose is sweeter than sugar, less is needed in order to attain the same level of sweetness, thereby making lower calorie foods. Now, let us talk about how our bodies take in fructose and how we use it as a source of energy, starting with the absorption process. The absorption of fructose is through facilitated diffusion, a process that uses transporter molecules but does not use ATP. Let me expound on this. GLUT5 is the main transporter located in the apical membrane of the small intestinal epithelial cells. It specifically and passively transports fructose from the intestinal lumen to the enterocyte. Once inside the enterocyte, fructose can be metabolized by the enzyme ketohexokinase to fructose 1-phosphate. This metabolism helps maintain a favorable concentration gradient for continued fructose uptake. Next, after absorption into the cytosol, fructose exits the enterocyte across the basolateral membrane into the bloodstream via GLUT2, also a transporter that moves glucose and galactose. GLUT2 facilitates fructose transport into the portal circulation, allowing it to reach the liver for further metabolism. Both GLUT5 and GLUT2 mediate facilitated diffusion, meaning fructose moves down its concentration gradient without energy expenditure, unlike glucose, which is absorbed partly by active transport mechanisms. This coordinated process ensures efficient, regulated absorption of dietary fructose in the small intestine, linking intestinal uptake to hepatic metabolism, which we will explain now. Let us talk about the hepatic metabolism of fructose. Fructose gets converted to fructose 1-phosphate with the catalyzing enzyme fructokinase with ATP. Fructose 1-phosphate then turns into two different products with the catalyzing enzyme aldolase B, which are glyceraldehyde and DHAP, otherwise known as dihydroxyacetone phosphate. Glyceraldehyde and DHAP can come back and form the same product called glyceraldehyde 3-phosphate, or G3P. G3P is also one of the entryways into glycolysis. Going back to glyceraldehyde and DHAP, these triose phosphate enter glycolysis after the PFK1 step, effectively bypassing this critical regulatory checkpoint. Because fructose metabolism bypasses PFK1, it is not subject to the same feedback inhibition that regulates glucose metabolism. This allows fructose to be metabolized rapidly and unregulated, even when cellular energy levels are high and glycolysis would normally be slowed. Continuing on with DHAP and glyceraldehyde, glycolysis isn't the only thing these triose phosphates are used for, as they also have uses with synthesizing lipids, triglycerides, and phospholipids. DHAP can be converted into glycerol 3-phosphate, which also serves as the backbone for triglyceride and phospholipid synthesis. This links carbohydrate metabolism into lipid metabolism, allowing cells to store energy as fat or build membranes. They can also be used to provide substrates for gluconeogenesis when needed. When triglycerides are mobilized, glycerol can be converted into DHAP, providing carbons for glucose synthesis during gluconeogenesis. Continuing on, while fructose metabolism can be versatile and efficient, it can have its own kinds of issues in the body as well. Continuing in our next tangent, fructose metabolism conditions. Let's talk about it. In your screen right now, you will see two fructose metabolism conditions, that being essential fructosuria and hereditary fructose intolerance. Let's start with the essential fructosuria. This is a condition when the body does not have enough fructokinase enough to convert fructose into fructose 1-phosphate. This, however, is a process that can be done by hexokinase instead, an enzyme that is used to convert glucose to glucose 6-phosphate. With the help of hexokinase, the body can instead convert fructose into fructose 6-phosphate. With this, it can still be used as a product in the glycolysis pathway for energy production. Since the work of fructokinase can be done by hexokinase instead, the symptoms of essential fructosuria are relatively benign, often asymptomatic. However, if this person does get testing in the lab, the lab will notice a presence of unconverted fructose in the blood or urine, which leads to fructosemia for blood and fructosuria for urine, respectively. Next, hereditary fructose intolerance. This is a aldolase B deficiency condition wherein the lack of the enzyme aldolase B prevents the conversion of fructose 1-phosphate into the products of glyceraldehyde and DHAP. This becomes a problem because the conversion of fructose 1-phosphate requires ATP along with the enzyme fructokinase. This incomplete process of fructose metabolism will have your body gain a net negative amount of ATP as the process goes on, which also prevents the processes of gluconeogenesis and glycogenolysis, as these processes need ATP as well. The stopping of these pathways will cause the body to have hypoglycemia or low blood sugar. As the saying goes, too much of anything will end up being bad for you. The same thing can be said for fructose itself. Excessive fructose consumption contributes to metabolic disorders through unregulated hepatic metabolism, promotion of visceral obesity, induction of insulin resistance, and altered hormonal responses. Let's expound on these. For unregulated hepatic metabolism, fructose is primarily metabolized in the liver, where it bypasses key glycolytic control points, leading to unregulated fructolysis and stimulation of DNL, or de novo lipogenesis. This process converts excess fructose into fatty acids, resulting in fat accumulation in the liver cells, which is a hallmark for NAFLD, otherwise known as non-alcoholic fatty liver disorder. Next, for the promotion of visceral obesity. High fructose consumption leads to postprandial hypertriglyceridemia. Again, hypertriglyceridemia, which promotes fat deposition in the visceral adipose tissue. This increases free fatty acid delivery to the liver via the portal circulation, further worsening hepatic fat accumulation, contributing to obesity and insulin resistance. Continuing on, fat accumulation in liver and muscle tissues trigger lipotoxicity driven by harmful lipid intermediates and activates inflammatory and stress pathways. This impairs insulin signaling pathways, leading to hepatic and peripheral insulin resistance. Excess fructose elevates uric acid levels as well, which promotes oxidative stress and endothelial dysfunction, further worsening insulin resistance and inflammation. Lastly, unaltered hormonal and unaltered hormonal responses. Unlike glucose, fructose does not stimulate insulin or leptin secretion effectively, which are hormones that regulate appetite and energy balance. It also causes smaller increases in GLP-1 and insulin, leading to less satiety or the feeling of being full, and increases promoting increased caloric intake and ultimately weight gain. Neuroimaging studies also show that fructose enhances activation of brain regions involved in reward and feeding behavior, which encourages overeating. In account of these effects, it is advised to lower dietary fructose, especially from added sugars and sugar-sweetened beverages, in order to enhance cardiometabolic health and lower the risk of obesity, non-alcoholic fatty liver disease, again, non-alcoholic fatty liver disease, and insulin resistance. Now, for the big question, fructose and glucose. What makes them different in a clinical context? In the clinical context, fructose and glucose metabolism differ significantly in their biochemical pathways, hormonal responses, and metabolic effects, which can influence cardiometabolic health outcomes. In your screen right now, here are some key aspects that differentiate fructose from glucose, starting with absorption and initial metabolism. Fructose is primarily metabolized in the liver via fructokinase to fructose 1 phosphate, bypassing the key regulatory enzyme PFK1 in glycolysis. This leads to rapid, largely insulin independent metabolism, in contrast to glucose, which is regulated by PFK1 and is strongly insulin dependent. Next, hormonal response. It is minimal to no insulin secretion, and this does not stimulate leptin significantly. In contrast, glucose is heavily reliant on insulin release and leptin production, which regulates the appetite and glucose homeostasis. Next, for glycemic impact, fructose has a low glycemic index, which is around 23. This causes smaller postprandial blood glucose rise, in contrast to glucose, which has a high glycemic index of 100, which causes rapid and significant blood glucose increase. Now, in the diabetes context, fructose metabolism is insulin independent, leading to better utilization in insulin resistant or diabetic states, but it may increase on uric acid and lipogenesis. In contrast, glucose metabolism is dependent on insulin, which is impaired in diabetes, causing hyperglycemia. In essence, fructose and glucose differ in their metabolic pathways and clinical effects. These differences influence their roles in metabolic health and disease. Fructose is an important sugar with roles found in both food and human metabolism. While excessive fructose intake has been linked to health issues, it is important to consume it in moderation. And that is all for my topic on fructose. This has been Aaron, your teacher from Hive Learning Center. I hope you learned something in this video and continue to learn more about all that is biochem. Bye bye.